Hi everybody, welcome to the next lecture, Audio Coding, this time in Outlook about parametric and generative audio. My name is Gerald Schuller. So first to parametric audio. So let's take a look at SAOC and MPEG. So SAOC stands for Spatial Audio Object Coding. So here, and this is actually part of MPEG. So existing spatial audio coders are channel-based, designed for a specific reproduction setup, for instance stereo or 5.1. But here this is about audio objects, so it's not about where the speakers are, but where audio objects are, for instance a singer or an instrument. So here we transmit audio objects instead of channel signals, and that's part of this standard here. So here you can see the system. So here we have audio objects instead of channels, and for the SAOC encoder, for instance, we can have a stereo or a mono down mix plus SAOC parameters. So here you can see it. Here we have an SAOC encoder. Here we have the different objects, for instance, a singer and different instruments. And then we have a down mix here. So this is actually all mixed together, like you would do in a studio, right? So you have different audio objects and then you mix them together as either mono or usually stereo, right? So that different objects appear in different positions in space, but even though you have many objects, you only need two channels in stereo to get you this spatial impression. And we saw that this position in space is encoded as interaural level differences or time differences as parameters. And these are the SAOC parameters, so they are actually more than ILD and ITD, and they describe the position in space. Then on the decoding side, we have the SAOC decoder, which tries to separate those objects. And then we have a renderer, which actually then does a downmix to the configuration at the receiver, be it stereo or 5.1 or surround, doesn't matter. So the important part here is that here the actual audio signal is just stereo or mono, so this can be compressed using the usual audio coders. And then we just have a few additional parameters which describe this complex scene, or rather the different objects here. So after this decoder we have some sort of separation, but observe that this is not a perfect separation. This is just good enough for this renderer to be flexible at different setups at home, for instance. Yeah, so here in the decoding side, the parameters are used to transform the downmix into audio objects, and then the rendering to loudspeaker configurations in the rendering matrix. Yeah, the advantages of object-based processing is, as I just mentioned, coding efficiency. The SAOC parameters are only a few kilobits per audio object, the additional parameters. And the coding and transmission is independent of the reproduction setup. So that's actually a big advantage because of the variety of reproduction setups you have. You can be, say, at home in your living room, you have a nice 5.1 setup. Maybe in some other place you just have stereo, or you just have headphones, right? Headphones are also quite common and is also conveniently possible with this setup. So here we can have this rendering on arbitrary loudspeaker setups, so not just 5.1, 7.1, 10.2 or 22.2, a binaural reproduction, which is headphones, wave field synthesis, which is even more speakers, and the rendering is also controllable using real-time user interaction. For instance, if you have, say, a sports report, you can choose how loud the commentator should be or how loud the environment noise. So you can actually choose at home. So that's a big advantage. You have a control over individual audio objects in this way. You can change the gain, equalization, you can add effects, and so on. So this is possible because you have more or less individual audio objects. Yeah, so this shows an example for the binaural reproduction. The binaural reproduction uses headphones, and it also uses head-related transfer functions, which is basically the transfer function of your ears, right? And this gives you a very good spatial impression because the brain is used to having this transfer function from your ears for a precise positioning in space. And this is taken advantage of by this binaural decoder. So here this rendering is integrated into decoding. So here we can see it. We have this downmix, stereo or mono. Here we have the SAOC bitstream, and here's the output with the help of the SAOC parameter processor and this downmix processor, and with the help of the head-related transfer function parameters. So this then gives us the optimum experience for headphones. Yeah, so here we have the HRTF parameters for binaural reproduction using an open SAOC interface, and this also enables the use of individual HRTFs because every head is somewhat different. So if you have your own HRTF, this gives the best reproduction. Otherwise you choose some generic HRTF and it still gives you a pretty good reproduction. Yeah, so this is for surround. So here you don't have headphones, but for instance you are at home in your living room and you want to have a multi-channel output, MPEG surround for instance. So here also the SAOC encoder works as a transcoder. So here we have the downmix processor. Here again the same parameter processor. Here we have the rendering matrix now, and we get the MPEG surround bitstream from and the process downmix together into this MPEG surround decoder to get the final output for the speakers. Yeah, it's also highly efficient. This also operates in the transform domain, as we will see in the moment, basically in the QMF filter bank domain, and it avoids unnecessary dequantization and decoding. Yeah, so the SAOC bitstream itself contains parametric description of audio objects, the SAOC parameters, and these are typical 2 to 3 kilobits per second per audio object, plus 3 kilobits per second per audio scene. And the SAOC bitstream is embedded in auxiliary data of the core audio coder, and this enables backward compatibility. Right, so this is actually quite convenient. If you have, say, a legacy AAC decoder, it can still decode the mono or stereo downmix. The parameters are transmitted in flexible time frequency grid, and this allows the adaptation to the bitrate to the demands of the signal characteristics. And we have the same time frequency grid as in MPEG surround. And yeah, we can also use it losslessly for efficient transcoding. So these are the SAOC parameters. As mentioned, we have the object level differences. That's the level relative to the loudest object. Then we have the inter-object cross-correlation. This is the similarity between pairs of objects. Then we have the downmix gain. These are the gains used in the downmix of individual objects. And we have the object energies. These are the absolute energy of the loudest object. Optional we have, this enables the merging of multiple SAOC streams. Okay. So here you can see how we can enhance audio objects. So we have This allows arbitrary attenuation or amplification of objects, for instance, for karaoke or for solo voices. The SAOC bitstream contains a residual signal, and we can reconstruct from a downmix and a residual. Right? And this has the efficient transmission of a residual signal using AAC. So this is when you want to improve a single audio object, for instance. So here we have the downmix. Here we have the bitstream and the rendering matrix and possibly the HRTF parameters here in the processor and the SAOC parameter processor. Here we have the SAOC downmix preprocessor. Then here we have this EAO contribution, and this gives us the output or multiple MPEG surround downmix. Right, and here's the MPEG surround bitstream. So in interactive remix or karaoke, we have interactive mixes. For instance, we get equalization or room simulation for individual objects. For channel-based formats, which is only applicable for the whole scene, we have a modification of specific audio objects, for instance, instruments or voices. And in this way, we can have karaoke or vocal solo. And we also suppress the main voice or background music. And this can be used to enhance audio objects. Further extensions of digital broadcasting is for clean audio dialogues or additional objects for interactivity. So keep in mind, originally SAOC gives you some separation of the objects. If you have better separation, you need additional information like the residuals that we just saw here. Yeah, and this is also important for teleconferencing. Today we have mainly monophonic reproduction, which is suboptimal for multi-user scenarios. And imagine you're sitting in a teleconferencing where several people sit on the desk. And usually it's not just one person talking, but often several people talk at once. And if you're in the real room, that's no problem because your ears can separate the voices. But if you do it in a teleconferencing setup, you need to have this spatial reproduction for your ears to be able to separate them. And this is also where SAOC comes in handy. So here we can also adjust individual speaker signals. For instance, we can have a speaker of interest and you increase the volume of that one. You can have this spatial representation of the audio scene where each speaker has its place in space. We can have an improved intelligibility and listening comfort in this way. And we can also have a match between the visual and audio scene. So imagine you have a large TV screen or display, and then you can try to map the voice origin to the place where the person appears on the TV. Yeah, and since we just transmit a mono or stereo downmix, this is very efficient and also backward compatible. Yeah, and here you can see a comparison with this listening test. So this is part of the MPEG verification test. We have 5 test sites, altogether 125 participants. We're using a Mashra test where you can rate the quality from bad to excellent in comparison to some hidden anchors, here the low pass version, and in comparison with different versions here. Yeah, so we simulate adjustments to a mix of audio objects, and the core coder is high efficiency AAC. So here HR is the hidden reference. So hidden reference is the original, which is important to detect if a listener can hear the difference or not. Then LP is the 3.5 kilohertz low pass version. Then high efficiency AAC ref is individual objects coded at high bitrate. Then here high efficiency AAC-MO is individual objects with the same bitrate. Then SAOC is the standard SAOC, and SAOC LP is for low power. And here you can see that here high efficiency AAC-MO, where we have the individual objects at the same bitrate, is lower, clearly lower than SAOC or the low power variant, which are both in the same range and better. Here is the HEAC reference, so this would be the full audio sources, so much higher bitrate, and you can see it's still somewhat better, right? But this would need a much higher bitrate. Yeah, here for the teleconferencing setup, this is part of the MPEG verification tests. Here the teleconferencing application. We simulate adjustments of a participant, and the core coder is MPEG-4 ELD. So here you can see we compare ELD for individual objects. That's if each speaker has its own coder. And here we use a CELD with SAOC low delay. And you can see they're about the same quality, even though we save 50%, more than 50% of the bitrate. So actually, this is pretty good. Same quality, but less than half the bitrate. Yeah, and that leads us to MPEG-H. This is a universal format for 3D audio, and it can also record higher order ambisonics, right? So this is a spatial recording format. It can use audio objects, which is track and metadata, and SAOC, similar to what we have seen. So MPEG-H includes SAOC, but also higher order ambisonics or channel-based formats for legacy. Yeah, and we can also replay as audio objects via the so-called vector-based amplitude panning. This needs geometry data, metadata, and one audio stream each for playing back in a certain position. Yeah, so what's interesting, what is higher order ambisonics? It's basically an extension of mid-side stereo to 3D sound. We have a recording with at least 3 directional microphones in different spatial directions. Remember, when we have stereo, ILD stereo, level differences, we have 2 directional microphones pointing into different directions. And then sound coming from different directions has different amplitude in the different microphones. Here we just extend it to a third one for the height, for instance. And we can also have more than just those 3 for improved directivity. So the directivity of the microphones can also be obtained by virtual microphones by suitably combining different microphone signals, for instance arranged on a sphere. So if you have a sphere, say 10-20 centimeters in diameter, and you place many microphones on its surface, and then you combine them like sum and differences, you get different virtual characteristics by this combining, and this also leads to a form of ambisonics, which you can also see here in this link. Yeah, so you can also have format converters. Here downmix for rendering. Here we have a mixer output of the signals, and in the QMF domain you then can generate the loudspeaker signals. And this is controlled by the mixer output layout and the reproduction layout to get the right loudspeaker signals. And here you can see the binaural reproduction. Observe that it's all in the QMF domain. So here we have QMF domain fast convolution. So this is important for the HRTF, the head-related transfer function. Then we have a sparse frequency reverberator and the time domain level differences processing here. This all is then here combined into this mixer and combiner to get 2 channels in 64 QMF bands for the reproduction. So they chose the QMF instead of the MDCT because the QMF has better neighboring band attenuation. Right? Remember here in this case we do a lot of processing in the subbands. So the goal here is not to reconstruct the original signal, but to have maybe one source attenuated and the other one amplified. And that means neighboring subbands can have very different factors. And in the case of the MDCT, this would lead to aliasing artifacts because of the limited attenuation in nearby subbands. But QMF, we saw, has very high attenuation starting at the subband after the neighboring subband. So you have much better attenuation of alias components in this way. And this is important here in this application. And that's why QMF filter banks are used, or rather PQMF. Yeah, and that leads me to the next topic. So imagine we have a parametric description, but no encoder. So this leads us to generative audio. And a very old segment is this called music-in. Music-in denotes a genre of computer music programming languages. And it started by music in audio programming languages by Max Matthews in 1957 at Bell Labs. You can read more here in this Wikipedia link. And later in the 80s and 90s, Csound was developed at the Massachusetts Institute of Technology, short MIT, and its Media Lab. And this influenced MPEG's structured audio orchestra language, or short SAOL. And this is still in active development and use. And you can also get an executable in Linux, which is called Csound. Right? And you can easily install it using sudo apt install Csound in Ubuntu. Right? And I have this little example here, oscills.scd. Let's try it. So here I have my little shell. Let's make it a little bigger. And first let's take a look what's inside. More oscills.csd. And here you can see it. It's basically a program which describes the sound. Right here we have the sampling rate, number of channels and such. And here we have oscillations. Here we can see the frequency, 220 Hertz. And that's basically it. Right? And we can actually then call this, give this program to Csound. Maybe I can try it again. It basically plays 2 times this tone. Yeah, and in this way you could also output much more complex sounds, synthesizer sounds or whatever. So this is good for generating audio signals, computer music. Yeah, as mentioned, this influenced structured audio orchestra language, SAOL. And this can also be used in Linux. It has this executable sfront, but it generates C code, which needs to be compiled with a C compiler to an executable to produce audio output. So it's actually not so convenient. And I tried it, and actually the C code executable doesn't really produce any sound. So it seems there needs to be some more to be done to make it audible. But you can also read more here in this Wikipedia link about it. Yeah, and then there's also Super Collider. This is very similar to Csound, but it has an IDE, so an integrated development environment. You can also get it in Linux with this command line sudo apt install supercollider in Ubuntu. And again, here you also have the problem with the sound output. Here you can solve it with a jack control, QJack control, and here you can select the correct output which should play the audio. So here in my case, I need to go to Setup, Advanced, Output Device, and then select USB audio. So then we can start the SuperCollider IDE with the Windows key and then search for SuperCollider IDE. Let me just do it. So here I'm using my Windows prompt, type SuperCollider, SuperCollider, here it is. So we click on it and then it starts. So you can see we have our IDE, right? And then to make audio work, we need to go to server and then boot server. Let's see if that works. So here we have server, boot server. Here you can see it's doing something, and here the green font tells you that now it is connected. And I have an example sound file, brook.scd. So let me see if that works. Open, and then brook. Here we have the brook.scd. Yeah, so here you can see the code. So again, you program the sound, and here you can see it's a combination of filters and noise generators. Filters at certain frequencies, and play then tells the system to play it back. And to play it back, you need to hit Control Enter. So let me try. Yes. So here you can see this noisy sound, which sounds like a little brook, right? So I found that was a nice example. And you end playing back with Control Dot. So you have to know those shortcuts, otherwise you don't enjoy it, right? And also this trick with the server and the jack. So it's actually not so straightforward, but once you have it running, it's actually quite convenient. Yeah. Right, and in case you want to generate speech, there's text-to-speech, right? This is also generative audio. It's just not an instrument, it's speech, for instance, also a singer, right? And actually modern text-to-speech systems are already so good that they cannot be distinguished from a human speaker, right? And examples are the voice assistants from Apple, Amazon, or Google, right? So their answer is generated by text-to-speech. And in this way, you could actually build an extreme low bitrate speech coder, which for the encoder would have a speech recognizer, turns it into text, and then the decoder would turn this text back into speech, right? And the bitrate of pure text is less than 100 bits per second. So in this way, you could have an extreme speech coder. But you may also want to have a robot-like speech, and in Linux you have the program Espeak, and in Ubuntu you can install it with apt install Espeak, and then in terminal you just type Espeak and your text. So let me try it. So I say Espeak, and then the argument is simply the text. Hello, I am a robot. Maybe I'll try it with an exclamation mark.
Hello, I am a robot.
Yeah, so here you can see the robot voice. So maybe the talking was a little bit fast, but it actually has options for the speed. You can actually reduce the speed, increase the speed as you wish. You can also have different voices, male, female, and you can also change the language. So this also works, for instance, for German. So that's quite nice. Yeah, and then we have machine learning, generative audio with machine learning. And this is actually an entire new field which opens up with generative audio using machine learning with neural networks. An example is the so-called variational autoencoder, or short VAE. It consists of a neural network as an encoder into a lower dimensional so-called latent space. So in audio coding, we say this is the encoded signal, right? Latent space is basically the encoded signal. So basically this comes out of our analysis filter bank, and then noise is added, just like quantization noise, right? So this is also like in audio coding. After our filter bank, we have the quantizer, and this quantizer is controlled by the psychoacoustic model, which tells us how much quantization noise we can afford. So this is basically the encoded domain with fewer samples and bits in audio coding. Yeah, and this is followed by another neural network as a decoder, which tries to reconstruct the original audio signal from the latent representation as good as possible. The system coefficients are optimized or trained by minimizing the reconstruction error while maximizing the added noise, or more precisely getting it close to a target of unit standard deviation. So this is like minimizing the bit rate by maximizing the quantization step size. And after training, one can input some random variation into the latent space to obtain loose sounds or noisy sounds, whatever. So here's a Python example from our project workshop on machine learning for audio signals in Python. So the encoder consists of two filter banks, the convolution or convolutional layers. So in machine learning, the terminology is somewhat different than in signal processing. So what we call a filter bank, they call a convolutional layer, right? And what we call downsampling, they call stride. They also add a 10H function, tangent hyperbolicus, nonlinearity, and this keeps the sign at the output. So it's basically like a saturation function. It doesn't go above 1 or below -1. So the first filter bank then computes the subband signals, which we call the mean value. And then there's the second parallel filter bank, which computes the standard deviation of the noise that can be added in each subband, which is similar to the psychoacoustic masking threshold. Right? So this basically acts like our psychoacoustic model. And this also has a nonlinearity at the output, but with an ABS to avoid negative outputs, right? Because the standard deviation is always positive. Yeah, and then in the decoder, noise with the standard deviation from the standard deviation network is added to the mean subband signals. So this is like added quantization noise according to a masking threshold. Right, so there's also this parallel to audio coding. So this is then input to the decoder synthesis filter bank, the transpose convolutional layer, with upsampling, again, the stride. And observe that all the filter coefficients, which here called the weights, are part of the optimization, which is here called training. So this has similarity to our optimization of the filter banks. Remember, we optimized the MDCT and the QMF and got optimized versions of it. But there we only optimized the prototype or window function. So we had fewer weights in this sense. Here we optimize all the filters separately. So we don't assume to have a modulated filter bank, but really have separate filters in this convolutional layer, which has orders of magnitude more coefficients to optimize. So this makes it much more difficult for the optimizer. So it's actually amazing that we get something useful out of it. But it does work. If you have a powerful optimization and a good machine, a fast machine for optimizing it, and enough time. Right, so this is actually different from what we did in audio coding. Much larger optimization problem. Yeah, so here's this example. PyTorch audio variational audio auto encode. So let me take a look at it. So here is the terminal for our workshop. Let me increase the font somewhat here. And let me open this file here. Gedit. Yeah, and you see that I'm using PyTorch. So it imports Torch. So I'm using PyTorch for the implementation. Here you can see this function turns our NumPy signal arrays into PyTorch arrays with a correct dimensionality, because here in PyTorch also always wants to have a batch dimension and a channel dimension. So I needed to add it. So this channel dimension would be useful if you would have stereo, but here I'm just using mono. Then the next is the class definition for convolutional autoencoder. And here you can see I have two convolutional layers. One for the mean. This is our usual MDCT, for instance, that we have in an encoder. And one for the standard deviation. So this takes on the role of our psychoacoustic model. Right, and then here for the synthesis, we have this transpose convolutional layer, as you can see here. Right, it has the same channel setup, but it is the synthesis filter bank. And here you can see we have in comes one channel, so this is our mono audio input. Out comes 32 channels, so we just keep 32 channels, but the kernel size here is 8 times 2048, so it's actually over 16,000 length. And we have a stride of 8 times 1024, so this is actually corresponding to an MDCT of about 8,000 subbands, of which we only keep 32. The most important 32 we keep. So this basically leads to a much lower dimensional latent space. Yeah, so this padding here I'm just doing to get the same size out. So this is basically like padding for a causal filter bank. Yeah, similar here for the synthesis, for the reconstruction. And here you can see the encoding function. Here's the function for the mean. Here we also get this 10H. This 10H actually helps for the optimization. Here we have our analog to the psychoacoustic model, where we have the apps 10H. And here we have the decoder, which is just the synthesis filter bank. Right, and here in forward we have everything together. We have the encoder, mean, standard deviation. Here we do adding the noise, mean plus here the standard deviation from the network times Gaussian distributed noise. Right, here we get the same shape as from the output of the standard deviation network. So each subband gets a standard deviation, and then we just add Gaussian distributed noise with this standard deviation. So here then this variational, Y variational, is then the noisy subbands, and then the decoder decodes the noisy subbands. Right, and Y pred is the reconstructed signal. Yeah, here I'm having two choices for the variational loss, basically to make sure that we don't have too much or also not too little noise in the subbands. And here's then the actual main program which executes everything. First I'm showing here the loss functions, the different loss functions. Here I'm reading two sound files, two speech files, which I actually use for two batches. So each file here is one batch, so it's actually a tiny batch. Here I'm converting them to PyTorch tensors. Here I'm defining the loss function for the reconstruction. So I'm using the mean squared error loss for the reconstructed audio signal. So the reconstructed audio signal should be as close as possible to the original in the mean squared error loss. Remember, in case of audio, this is actually not optimum, right? We know that the mean square error loss is not a good loss, but nevertheless, this is the usual for variational audio encoders, and probably you can improve it a lot by having a more suitable loss here. Yeah, here's then, here I call the model. So the model basically is calling the forward. So let's see, where did we define the model? Where is model? Here. So model equals conv autoencode. This is the class that we just defined. So then model is an instance of this class. And we can also port it to device. So for instance, if we have a GPU, which I don't have here. Right, and here we just call model for the first time. Then it needs to be optimized, and the optimization loop is here. So I'm using 2000 iterations here. And here you can see I'm computing the analysis. Here the noise from our noise model. Here is the noisy version where I add the noise, and here I'm applying the decoder. Ypred is the reconstructed signal. So then we compare Ypred with Y. Y was the original signal, and Ypred is reconstructed. And this is our mean squared error. And here we have our variation loss, right, for the noise. And then we combine both into this loss function, the mean squared error plus some factor times the variation loss, and we choose this factor such that both of those components have a similar size. And then we feed it into this optimizer. This tries to update the coefficients. Optimizer 0 grad basically sets the gradients to 0, and then it does the backward loss backward, which is computing the gradients in the network, and here it's doing the update of the weights using the gradient here. And after 2000 steps, we save the model and then we play the result. Right, and then we try it out on the test set and also have a third for first on the training set and then have a third for the testing. So let's start the optimization. This will take a moment. Copy. So here I'm starting it. So here you can see the two versions, and you can see here the loss for the variational. The variation loss becomes minimum around 1. So it tries to get the noise as close as possible to a variation standard deviation of 1. Yeah, now it's doing the optimization. You can see here the step, and here the different parts of the loss. Here the mean squared error loss, here the variation loss. Both we want to minimize. And here you can see why we needed to have this factor of 0.01, because the values here are about 100 times as big as the values for the mean squared error. So what we will see here is the two speech files for training, which we call batch 0 and batch 1 for training, and then there's another speech file for testing. So extra speech file for testing. After training, the two speech files for training are input into the variational autoencoder with and without added noise in the latent domain. So basically this is like turning on and off the quantization. And then the same is done with the third speech file. So first displays the test speech file, and then also with and without noise for the decoder. Yeah, and this program also has text-to-speech announcements using eSpeech. So you should carefully listen to the announcement to hear what it plays next. So first here you can see the result after optimization. So here we can see encoder analysis filter 0, which is the standard deviation, and here for orange and blue means the mean, so it's kind of hidden here, and green is the decoder filter 0, the output of the decoder filter. So yeah, you can see here these are the filters basically, and you can see they don't really look like an MDCT, right? So it's kind of amazing that this works at all, because the filters that we see are more like noise. When I zoom in here, you can see the different filters. So the blue and the orange, but it's hard to see any structure here. So here the outputs, the encoded domain. Here you can see the encoded domain, and orange is the encoded standard deviation, and you can see here the standard deviation is indeed very close to 1, as was the target, right? So that basically it means it found a system such that we add this noise, the output is still as close as possible to the original. So it's having a good reconstruction in the mean squared error sense. So let's close this. Here now we have the target and noisy predicted signal. So predicted means reconstructed. So here the target is the original, the blue, and the orange is what comes out of our variational audio autoencoder. And I can zoom in, and you can see it's actually not so bad, right? Despite the added noise, it's actually quite close to the input.
The training set output for clean encoded signal for match 0.
Dies ist ein Test. 1, 2, 3, 4, 5, 6.
The training set output for noisy encoded signal for match 0.
Dies ist ein Test. 1, 2, 3, 4, 5, 6.
Yeah, this is for the next batch. We have again the encoded mean in blue, and here the encoded standard deviation, which we see is also quite close to 1. Here we can see for batch 1 the reconstruction is not quite as good. Here blue is the original, the target, and orange is the predicted, the output of our variational autoencoder. So let's listen to it.
The training set output for clean encoded signal for match 1.
This is a test. 1, 2, 3, 4, 5.
The training set output for noisy encoded signal for match 1.
This is a test. 1, 2, 3, 4, 5.
The verification set input to the variational autoencoder.
Dies ist ein Test. 1, 2, 3, 4, Test.
The verification set output for clean encoded signal.
Yeah, so here this is for verification, or what I called here testing. So you can actually see both. Actually often testing is done for optimizing the network, and verification is the final test, so to speak, or verification. And here you can see, here it doesn't really work so well, right? Because this is an unseen signal, which you didn't see before. And you can see it's actually quite different. And this is also what we heard. The input was a different speech. Then didn't really matter if I added noise or not. It was always kind of hallucinating sounds. So
The verification set output for noisy encoded signal. Only noise as encoded signal. The decoded signal.
Yeah, so the last two examples was the noisy version, so sort of quantized version of the verification set. And then the last one was just noise as input. And you found even if I just have noise in the latent space, no input from, no audio input, it still sounded the same. So it kind of hallucinated voices. So, and this is kind of an interesting property of variational autoencoders. The network can hallucinate, and that makes noise in the latent space sound like another speech signal. And this is also a way to hide quantization noise, right? If quantization noise doesn't sound like quantization noise, but like another audio signal, then it's inconspicuous, right? People don't really feel that it's an artifact, but maybe it belongs there, right? So it's kind of another way to hide quantization noise. And that also what makes it interesting. Yeah, here I have some references. First, this book from Eugene Charniak, Introduction to Deep Learning from MIT Press from 2018. And then here our website on the project workshop on machine learning for audio signals in Python. Yeah, and that's it for today. Thank you for your attention. And then, yeah, good luck everything.